Yes, I can hear you.
Okay.
Thanks for the wait. We have a communication problem.
Yes, I can hear. Okay.
Great. Nice to meet you.
Okay. Nice to meet you.
Okay. This seminar will be broadcast on YouTube, and I'm gonna present you a little bit in Spanish, and then I'm going to come back to English. Okay. I'm gonna. Okay. Hola a todos, bienvenidos al Seminario de Fronteras de la Energía. Hoy yo voy a estar guiando este seminario. Soy Araceli Cisneros, académico postdoctoral de nuestro instituto. Y hoy nos acompaña la doctora Claudia Prestigiacomo. Okay. Hi everyone, welcome to Energy Frontiers Seminar. Today, I have the pleasure of introducing Dr. Claudia Prestigiacomo, and I will read a summary of her professional career. Claudia Prestigiacomo is an assistant professor of chemical engineering at the University of Palermo. She earned her degree in chemical engineering from the same university in 2017 and complete her PhD in technological innovation engineering in 2021. Following this, in the same year, she undertook a postdoctoral fellowship focused on solar heating integration with industrial plants, followed by a second postdoctoral fellowship in 2022 on the electrochemical treatment of polluted soil. Dr. Prestigiacomo's main research areas include waste valorization through hydrothermal liquefaction processes, molten salt-based thermochemical processes, solar heating integration with industrial plants, biodiesel production from vegetable oils, and the technological development of high-pressure chemical and electrochemical devices. Today, she will talk about solar thermal technologies for the decarbonization of industrial chemical processes. With this, we welcome Dr. Claudia Prestigiacomo. Please go ahead.
Claudia, I think your microphone is turned off. Can you turn on, please?
Okay, I'm sorry, but my connection followed down. So yes, nice to meet all of you. So may I share my screen?
Can you try again?
Yes. I'm sorry, but I have to try again. Wait, just okay. Yes.
Do you have problems to share your presentation, Claudia?
Okay. Yes, I have to exit and come back because of the possibility to share the screen.
Okay.
Just
Go.
excuse me.
Okay, don't worry. Go ahead, please. Filiberto y Araceli, ¿tienen permisos de administrador para que también dejen entrar a la gente, ¿vale?
Sí, gracias.
Sí. Ok. Ya, ya, ya admití a Claudia de nuevo. Problemas técnicos, una disculpa. Ok. Welcome back, Claudia. Okay, your mic is turned off, so you please turn on, sorry.
Okay. Okay, so now I can share my
Yes.
screen.
You can share. Okay. Okay, nice.
Okay.
We can see your full desktop now. Okay, now we can see your
Can you
slides.
see?
Yes, now we
Okay.
can see.
Perfect.
No, don't worry, it's a common problem. So well,
Okay. So thank you. May I start already?
yes, you
Okay.
can.
So thank you for the nice presentation. Thank you for the nice presentation. As Dr. Cisneros told, I'm Claudia Prestigiacomo, an assistant professor from University of Palermo, and today is my pleasure to share to you, to all of you, the results that the research group of the industrial chemistry in Palermo obtained in the last years in the framework of concentrated solar thermal technologies for decarbonization of industrial chemistry processes. Okay. Okay, yes, I just skipped this slide since Dr. Cisneros already presented me, but I am quite young. I just follow up my research career in a very few years from 2017 to 2022. And nowadays I'm assistant professor and I am teaching in the chemical engineering course in the University of Palermo. In particular, my teaching activities are in the framework of treatment of gaseous effluents in the atmosphere. So, University of Palermo, few words because I think that most of you does not know the Sicily or Italy or some, in particular, University of Palermo. For us in Sicily, the University of Palermo is a very consolidated research institution that is located in the central western Sicily. There are many poles, not only in Palermo, that is the main city in Sicily, but also in Trapani, Agrigento, and Caltanissetta. This university is made from 16 departments and more than 100 active international research collaboration. For us, for all of us, in particular in the engineering department, we are really happy to prompt collaboration, in particular international collaboration. And in the framework of European Union, we can collaborate within Erasmus agreement with 44 European Union countries. About the industrial chemistry group, a few words also to describe our research activity in the history. The research group in which I work, the industrial chemistry group, is active since 1916, in that years Professor Ercoli and Mauro Guainazzi founded this laboratory, collaborating with the Polytechnic of Milan, and a branch of the industrial chemistry that in Polytechnic of Milan was developed in Palermo. In particular, our investigations were based always during the years in the development of the new technological chemical processes in the framework of frontiers in energy, frontiers in chemicals, frontiers in the development of new and fine chemicals. Now we are made from two heads of the laboratory, Professor Alessandro Galia and Onofrio Scialdone, and several group members like assistant professor, like Najwa Amdi, Federica Proietto, and Serena Ramdaz, that are my colleagues, and about 20 between PhD students and master thesis students. Our research investigation are developed in two branches. So like Dr. Cirneros told before, we are working in the two branch, chemical, industrial chemistry processes and industrial electrochemical processes. In particular, our focus is focused in the conversion of organic waste into value-added compounds and fuels throughout thermocatalytic conversions, for example, such as hydrothermal liquefaction or pyrolysis assisted by molten salts, or in the other side, interesterification and transesterification for the production of biodiesel. And on the other side, we developed pressurized electrochemistry cells in order to allow us to perform electrochemical modification of polymers or electroreduction of carbon dioxide to fuels and chemicals. And another side that was developed in the last years is the electrochemical treatment to treat marine sediments for electroremediation. Our focus is also in the reaction in using supercritical fluids like supercritical carbon dioxide and supercritical water that we use, for example, in the framework of the liquefaction in order to valorize organic wastes. But let's go to the focus of the today about the field that we started to investigate in the last 2 years in a more deep way, because in these 2 years we carry out a very intensive collaboration with Enea, that is the research center in Italy that is the most developed research center in the field of concentrated solar thermal technologies, in order to understand how it is possible to think to some strategies and perform the decarbonization of industrial chemistry processes. The outline of today will be constituted by first section, in which I will introduce the concept of the energy demand and carbon dioxide emissions in the industrial sector. And I will talk about some possible strategies that are currently adopted for the decarbonization of the industrial sector, and the possible role of solar heat. Furthermore, we will see the results that we obtained by the analysis of the integration of the industrial chemistry processes, thinking to use the solar heat. We case study in order to understand the impact of using solar heat in the crude oil distillation, so inside the refinery process, and to use solar heat in industrial processes, that is the thermocatalytic dehydrogenation of ethyl benzene to styrene. so a petrochemical process. I would like to highlight that the data that I will present to you today are published in 2 research papers. So, of course, today I will not describe in detail the methodology or the experimental scenario that we adopted. But for any doubt, you can of course contact me, and of course you can consult or download the publication that are in open access. At least the last part of the lecture will be focused on the main conclusions that we obtained and our future perspectives. So let's start about the energy demand of industrial sector. From the more recent report of solar payback, solar heat for industry, it is possible to see that up to 2017, the 32% of the total energy demand can be attributed to the industrial sector. As you can see from this slide, the most of these 32% is or can be derived to the industrial processes in the form of heat. If you look at the data presented in this report, you can see that most of this heat is currently fed to the industrial processes in the form of fossil origin energy sources, like 45% of coal, 30% of natural gas, 15% of oil, and only the 9% is constituted by the usage of renewable energy sources. Furthermore, if we look to the global carbon dioxide emissions in 2016, we can understand that from the 35 gigaton per year of carbon dioxide emitted, the 7.5 gigaton per year can be attributed to the industrial process heat. And in these 7.5 gigaton per year are attributed to the fossil origin energy sources because their combustion, of course, produce carbon dioxide that is released in the atmosphere. If we have a look to the 74% of it, and we consider the fragmentation of the applicative industrial process, we can also think about divisions of the kind of heat that we have to drive to the industry. Because if we think, for example, to boiling plant, pasteurizing, sterilizing, or food industry in general, we can think about the low temperature heat. So heat request, heat demand that can be used below 150 degrees. If we think to other processes like distillation or compression or dyeing or melting, we can think about heat from 150 to 400 Celsius degree. But there are several other applicative industrial processes that require high temperature heat. So an heat that has to be driven to the chemical sector temperature up to 400 Celsius degree. And in particular, this sector involve the material transformation processes. So all the petrochemical industry and the chemicals productions. Nowadays, several possible decarbonization strategies for the industry, it is possible to carry out. For example, if we look at this slide, I reported the data about the possibility to prompt the electrification of the chemical industry. If you see in the remap case in 2050, we can see that 42% of electricity can be shared in the final energy use. But if we think in the industrial sector and we think about the fact that chemical and petrochemical and steel are among the largest emitters, they use high temperature processes. So we have to consider that for that this sector is difficult to decarbonize, and not only electrification that is very, very expensive and expensive strategies can be used to prompt this decarbonization. In particular, we can focus the attention to other kind of energy sources to help the cheap as possible decarbonization strategies. For example, biomasses, solar heat, geothermal, and heat pumps requirements. In the framework of renewables energy sources to prompt the decarbonization, our work was focused to use the solar heat, to exploit solar heat as a decarbonizing agent. In the collaboration with the Research Center Enea, we adopted the strategies that you can see in this slide. In particular, the aim of these strategies was to use a solar field constituted by tubular collectors. Inside these tubular collectors, it is possible to flow a liquid heat transfer fluids, and these heat transfer fluids can be stored, can be collected into two separated tanks. As you can see from this slide, the red tank is constitutes the hot thermal energy storage. Instead, the orange storage tank can store the cold fluid, so the fluid that has been used to feed the solar collected heat from the tubular collector to an heat exchangers network. So at the exit of the heat exchangers network, the liquids heat transfer fluids exchanged the collected solar enthalpy, and it is like so-called cold fluid. It is stored, collected in the cold tank before to be sent again in the solar field and and collect again the solar heat. In this case, the liquid heat transfer fluid can be modulated and can be decided in the way that you have to drive a low temperature heat. For example, application in which you can use also water or steam in order to or hot water, compressed water to feed these kind of strategies. If you have to work at medium and high temperature, you can substitute the liquid hot water with thermal oils or the molten salts mixture. In our case, the first case study that we started to investigate was considering the crude oil atmospheric distillation, in particular, of course, the so-called topping unit. Why we decide to prompt and start this case study? If you think to the refinery sector, the most energy demanding one of the most energy demanding part of the refineries is constituted by the distillation, the atmospheric distillation of crude oil, and in particular from 30 to 40% of the total energy demand of the refinery has to be fed to the topping unit. And of course, this energy demand, it is depending from the capacity of the refinery. And if we think to the Sicily realty, that was the realty that prompted us to start this investigation, is a particular situation in which our refineries that we have in the eastern part of the island treat more or less 10 billion of tons of crude oil per year. So there are very huge industrial units that has to treat more or less 900 of tons per hour of crude oils. And of course, the energy consumption depend on the size of these units. So, a mandatory strategies in the development of the refinement technologies was to carry out a heat integration among different processes, and by doing this heat integration, we can use the heat of the products like naphtha, kerosene, gas oil, and EV oil to preheat the crude oil. And the final heating of the crude oil is nowadays reached using an horizontal furnace, in which fuel gas or oil can be used for turn on the furnace and allow us to obtain a crude oil that reach more or less between 340 and 360 Celsius degree before to enter in the distillation column. Our strategies was thought starting from the data of the real refinery that is located in Milazzo, in the north part of the island, near Messina. And in particular, this refinery is constituted by two units for the crude oil distillation. The one that you see in this slide, Unit 1 and Unit 2 in the bottom part. The design capacity of Unit 1 is around 1,000 tons per hour. And if we look at the furnace that has to be turned on to get operative the Unit 1, its thermal power is around 130 megawatt. And the used in our case study, the fuel used for the burners is methane. If we look at the Unit 2, its design capacity is around 800 tons per hour, and the required furnaces has an operating thermal power of around 100 megawatt. And in our case, we assumed that these furnaces is fed by 80% of fuel oil and 20% of methane. The refinery of Milazzo has these two topping units in order to treat two different crude oil. So for them is very mandatory to continue in operating these two units in a parallel mode. So they in the framework to propose some decarbonization strategies to the topping section, they would like to think to these two parallel units because they require to treat the two different crude oils in parallel. So starting from this assumption, this condition, we proposed to investigate a network doing like this that I show in this slide. As you can see, there is a solar field in the left side of the slide, and from this solar field, tubular collectors are filled by molten salts mixture, and these molten salts collect the solar heat, and it is sent to a hot thermal energy storage that works at a nominal maximum temperature of 550 Celsius degree. From this tank, we considered several scenarios. In particular, we considered the scenarios that are reported in the right side of the slides, in which in the first we use the molten salt mixture to drive two molten salt heat exchanger network. The first on the top, that is the one that we coupled to the furnace in the unit 1, and the second that you can see in the bottom part of the slides that is joined to the furnace in the unit 2. The scenario 2 is the one in which we our hypothesis is to feed the molten salt mixture to the molten salt of heat exchanger of unit 1, sorry, and the last scenario is the one that in which we drive the hot molten salt mixture to unit 2. As you can see from the data, we obtained a thermal power reduction of 29% when we divided the solar heat, the collected solar heat, dividing the molten salt mixture in the two heat exchanger networks. We analyzed the sustainability and the feasibility of the scenarios, considering the savings percentage of carbon dioxide per year. And in particular, the most favorable scenario was the scenario 1, in which you can see that the saving percentage of carbon dioxide was around 13% in Milazzo. Then we continued this investigation because we thought that probably Sicily is not the place, is a very sunny place, but maybe in the all the earth we can have some other places in which we can exploit better the sun radiation during the years. So we compared the scenario using the ANI distribution over the years of Milazzo with the United Arab Emirates, in which we can have a better distribution of ANI over the year. And so by doing this substitution, considering that the refinery can be located in the United Arab Emirates, maintaining the same considering scenarios, we obtained a reduction of 19% of carbon dioxide emissions per year. Then, following this assumption, we continued our case study, and in particular we considered the fact that, okay, in our case, our decarbonization strategies till now worked on reducing the methane or the oil that we used in the furnaces. And by reducing this fuel consumption, we obtained a reduction of carbon dioxide emissions. But what's up if we work in decarbonizing, refining, and decreasing the methane consumption in the methane reforming units? Because the methane reforming units is a very, very energetic demand, since the hydrogen till now is commonly and mostly produced by crude oil. So in our case study, we did the hypothesis to cover the same land that we considered that using tubular collectors with the photovoltaic panels, and to use the photovoltaic panels to drive the electrolysis, the PEM electrolyzed cell, in order to produce hydrogen from water electrolysis instead reforming of methane. And by doing this consideration, by evaluating the rate of return of the investment of the better sustainable scenarios, we obtained that if we assume an ideal conditions in which the energy consumption for hydrogen production is very ideal without ohmic resistance and so on, and we consume 3.17 kilowatt per hour per normal cubic meter, we obtain a rate of return of investment that is a little bit lower the rate of return of the investment that we obtained with the best scenario by using concentrated solar power plant. If we consider a real energy consumption that we found in literature, we obtain a significantly lower rate of return of the investment. And this data of course, allowed us to assume promising the decarbonization strategies throughout concentrated solar power plant. So, what about the main achievements in the case of solar crude oil distillation? From one side, we developed the hybridization strategies, finding that in Sicily we can save more or less from 11 to 13% of the total greenhouse gas emission of the considered methane fueled unit. But if we look at the United Arab Emirates, we can increase this percentage to 17 or 19 of the percentage of the total greenhouse emissions of considered methane fueled unit. Then, if we compare the hybridization scenario with another scenario in which we can cover the same land with photovoltaic panels, and we can decrease the amount of methane, not fueling less amount of methane to the furnaces, but using less methane to produce hydrogen, we found that the rate of return of the investment is higher in the case of the better strategies that use concentrated solar power plant. Now we can spend other words in the framework of the thermocatalytic dehydrogenation of ethyl benzene to styrene. Another case study that we carried out was based on the consideration of very energetic intensive industrial processes to produce commodities. Styrene is a chemical commodities, and the production volume of these commodities is around 31 megatons in 2018, and this amount is expected to grow up to 36 megatons in 2024. Commonly, the styrene is produced by the hydrogenation of ethyl benzene and producing styrene and hydrogen. This reaction is a very endothermic reaction, and it is industrially carried out in both adiabatic and isothermal reactors. Our case studies started from the consideration of a patented plant and developed plant by BASF to carry out the isothermal dehydrogenation of ethyl benzene, and that you can see the scheme in this slide. In particular, this interesting option was carried out using shell and tube reactors, and shell side, as you can see, there is the recirculation of the flue gas or molten salts. So the already present technologies use the molten salts to drive the dehydrogenation of ethyl benzene to styrene. But in these strategies, the molten salts were heated up using conventional furnaces. Our case study was developed starting from these technologies. And we studied also the possibility to couple the same isothermal reactors with a solar field, the same strategies that we used in the crude oil distillation, and the same strategies developed by INEA. So in this field, the strategies was to substitute the furnace with a concentrated solar power plant in order to use a molten salt mixture as heat transfer fluid. And using this energy vector, we can decarbonize, or we can study the decarbonization of the energy intensive ethyl benzene dehydrogenation. As you can see from this slide, we used a distribution of ANI of Priolo in Sicily. That is one of the main industrial pole in Sicily, industrial center. By doing this analysis, what we obtained is distribution of carbon dioxide emissions in the case of the plant is totally driven by a methane combustion, so the conventional plant that you can see in the dark blue bars in this histogram, and the plants hybridized with the concentrated solar power plant, changing what? We changed the numbers of solar collectors. So as you can see from the bars in with lines in dark blue are considering increased number of solar collectors. So what we obtained is that increasing the number of solar collectors, we decreased the carbon dioxide emissions if we look at the tons per month. So over the years, you can see a decreasing for each month, increasing the number of solar collectors. If we look at the overall savings of percentage of the carbon dioxide emissions per years, we can see, in fact, that the case of 100% allow us to reach among 60% of carbon dioxide reduction. But in order to investigate the economic sustainability of this scenario and to assess the most economic sustainable scenario, we conducted an economic assessment by considering some figure of merits, like the annual normalized gain value, or the rate of return on the investment, and discounted cash flow rate of return. As you can see from the plot, you can understand that in our case, the discounted cash flow rate of lines and pointers, and you can see the values on the right side of the plot, is around 11%. So we looking at the state of the industrial data, we found that the common used range, common obtained range of variation of the discounted cash flow rate of return is from 5 to 10% in the case of 130 business units of chemical processes upgraded with new technological innovation. And our case studies are a little bit higher we obtained a little bit higher value with respect to the one that is commonly obtained. So this prompted us to consider very, very promising these scenarios. And by concluding this investigation and introducing our future perspectives, what we can say? We demonstrated that the decarbonization of chemical and petrochemical processes is, of course, an important goal because we would like to make very sustainable productions, in particular sustainable productivity of chemicals and goods. And of course, we have to consider that up to now, it is very difficult that, for example, most of the goods that we obtained and use in nowadays can be substituted. If we look at the styrene production, we use very effectively consideration because we use a conventional shell and tube fixed bed reactor, and we considered to hybridize this reactor with a concentrated solar power plant in order to investigate the possibility to drive by solar heat the high energy intensive process. In particular, we found that with the best scenarios, with the numbers of collectors between 60 and 70, the carbon dioxide emissions can be really decreased till 50%, and obtaining a return of the investment that is a little bit higher with respect the data found in the literature, in which we can see the investigation with the sustainable modification of the technologies. And in particular, if we focus the attention to the topping units, we found that also in that case we can achieve 11% of carbon dioxide emissions for each unit, and this percentage increase if we move to a place in which the sun radiation is more mitigated over the year. And it has to be considered that for the refineries, talk about 1% reduction of carbon dioxide emissions per year is very, very significant. And you can see it because it is written also in the annual report of sustainability of the refinery. They always is detailing the amount of carbon dioxide that is to be reduced over the year. So to conclude, we can say that the outcomes obtained by studying solar topping and solar stirring demonstrated us that use concentrated solar heat can be a very effective option to decarbonize energy-intensive endothermic chemical processes. And our future investigation will be focused on continuing the investigation of the possible strategies to couple concentrated solar heat technologies with industrial chemistry, and in particular from very few years, we are conducting some other experimental activities in order to valorize in the same reactors organic waste by using molten salts as not only carry heat exchangers, but as solvent and catalyst inside the reactor. So the future perspectives are very, very demanding. And with this, I would like to thank you for your kind attention. And if you would like to ask some other questions, you can do also, of course, now, but you can contact me using the email.
Okay, thank you very much, Dr. Prestigiacomo. We have a few minutes if someone wants to ask something. In the YouTube channel, we expect a few questions, and I do have a question. This part of the solar steering production, what kind of technology do you use?
In the solar concentrating solar heat, you say.
Yes, the solar steering, the thermocatalytic dehydrogenation.
Oh, okay, yeah. The kind of reactor or the kind of solar field?
The solar field, I mean the concentration solar power technology.
Okay, yeah, we used the tubular solar collector, parabolic, and it is a line of a tubular collector with a parabolic lens, and the tubular collectors are placed in the middle, and these like loop of tubular collectors are like design parameters for us, because if, for example, you can see that my screen.
Yes.
Can you see my screen? Okay, so if you look to this P&I, we have the reactor that we know the capacity of this reactor by considering a typical dehydrogenation of a steering units plant, and by knowing the capacity of these reactors, we can consider a nominal power required by the reactor. So by considering this nominal power, we can design the solar field by simply considering the analogies of power that is required by the reactor. And the technological improvement in the solar field is to change the number of solar collectors, so the number of loops that you have inside this solar field, in order to collect more sun radiation. The technologies is like okay, like this.
Okay. Okay, got it. So I'm asking this question. Have you ever think about using another kind of technology?
Yes, we considered, like in the case of the crude oil distillation, in which we changed completely the technologies to decarbonize, because instead of concentrated solar power, we use photovoltaic panels in the additional scenario. Of course, we are open to consider other technologies, and we started with these strategies because of the collaboration with Enea that is in charge in Italy with this kind of of the technologies. And currently there are few plants developed by Enea in Egypt and in United Arab Emirates that use these kind of technologies. So in a first attempt, we use these technologies because is already developed in the industrial case, in industrial scale. But of course, we are open to consider other promising technologies.
Okay. I asked that question because here in the Institute, we have a group working with this kind of processes using solar concentrated power. Actually, we have a huge solar furnace that we use for these thermochemical processes in another process. So we expect we can collaborate in the future with your group.
Yeah, it will be a pleasure for me. It's like a thermochemical reactor in which the sun radiation is concentrated in the reactor, direct radiation.
Yes, we do that process.
Okay.
So that was my question about, because you need
Okay.
thermal energy.
Yeah, in our case, the only difference is the fact that with using recirculation of molten salts, you can store the molten salts in the hot tank. So you can use this strategy also in the evening, also in the night.
Right. Right. Okay, thank you. We have
You're
another
welcome.
question. Dr. Ramos, go ahead, please.
Thank you very much for the very nice presentation. I was wondering if you can comment on the possibility of using this kind of alternative source of energy, but in applications that are at a higher temperature. Let's say not 200, 300 degrees centigrade, but go all the way up to 1000 or 1500, in the sense that I think that in those cases, the availability of energy would be far more expensive. And so it would be very convenient to use, say, a solar concentrator, which can reach these temperatures. So can you comment a little bit on this, please?
Yes, of course, as you thank you for the very specific questions, and this is the point. So the requirement of temperature is very important, and lets us to like make a decisions to the applicative point of view. We, for example, selected the hydrogenation of styrene because it's a chemical process. A processes that is carried out usually at 700 degrees, and we understood that by coupling these technology with the concentrating solar thermal technologies, we have a temperature limitation of 550 maximum operating temperature of a concentrating solar plant. And so we understood that this, of course, caused a decreasing of productivity of the industrial plant. So I think from my point of view, at the end of this consideration, that if we would like to think to feed energy and the heat to higher temperature, like 1000 or 1500, as you told, we have to think to other technologies, because if we consider of course, the design parameters of a concentrated solar plant, the very big limitation is constituted by the materials that you are using. For example, molten salt starts to the most commonly used molten salt mixture starts to degrade at 600 670 Celsius degree. If we use some other particular mixture, we can use the molten salts till 800, but of course, at 800, the tubular collector starts to have problems for bending and for resistance of the materials. So I think that the challenges are a lot in this field if you would like to think to decarbonize very high temperature processes.
Thank you very much.
You're welcome. Thank you for the question.
Okay, thank you. There's no questions on YouTube channel. If anyone else want to ask. I think they're not. So with this, we finish our seminar. We thank you very much, Dr. Claudia Prestigiacomo, to join us today and for your time. So goodbye to everyone joining us today, and we see you next week.
Thank you. Thank you for the opportunity and to meet you, all of you. Thank you.
So Araceli, we can close this, right? Okay, we can stop sharing the
Okay.
YouTube and all. Okay,
Okay.
thank you.
Okay. So we are done.